Hello students, let us study about ozone. So ozone is O3 and you know it's an allotrope of oxygen. So let's see the preparation, how ozone is prepared. So ozone is prepared from oxygen. So when oxygen gas is passed through electric discharge, ozone is formed. So the product ozone is formed from oxygen. So when it is passed through an electric discharge, so this product is actually called ozonized oxygen. This product is called ozonized oxygen. Now let's see the properties. First one is color of pure ozone. Color of pure ozone, if it is in the gaseous state, it is pale blue. It is liquid state, it is dark blue. If it is in the solid state, it is violet black. Then the smell, it has a characteristic smell. And the concentration, if the concentration of ozone is small, it is harmless. But if the concentration is more than 100 ppm, 100 parts per million, it is harmful and it may cause uncomfortable breathing, headache, nausea, etc. So the concentration is more, it is harmful, and if it is small concentration, it is harmless. Now let's see another important property, that is ozone is thermodynamically unstable. So it's an important question, why ozone is thermodynamically unstable. So let's see the answer, that is when the decomposition of ozone to oxygen, if there is decomposition of ozone to oxygen, the reaction is highly exothermic. The reaction is highly exothermic. That means delta H is negative. And we know that the gaseous species increases. So 2 changes to 3. So therefore, we can say delta S is positive. So from the Gibbs energy equation, delta G is equal to delta H minus T delta S. So delta H is negative and delta S is positive. Here we will get a high negative value. So there will be a large negative value. There will be a large negative value in the Gibbs energy change. So the Gibbs energy change is a large negative value. So we can say that this is a spontaneous also. This is spontaneous. So we can say the more concentration or high concentration of ozone is dangerously explosive. So this is how we can explain ozone is thermodynamically unstable. Now let us see another important property, that is ozone is a powerful oxidizing agent. Ozone is a powerful oxidizing agent. Why? So that is another important property of ozone. So that is also a question. Ozone is a powerful oxidizing agent. Why? So here we can say ozone is converted to oxygen and it produces nascent oxygen. So nascent oxygen means it is newly born oxygen. So the liberation of nascent oxygen is there in the decomposition of ozone to oxygen. So in this decomposition process, the liberation of nascent oxygen is there, and actually this nascent oxygen helps in oxidation. So the oxidation of ozone is due to the liberation of nascent oxygen when ozone is decomposed to oxygen. So let's see some oxidation reaction of ozone. The first one is when lead sulfide on oxidation in presence of ozone produces lead sulfate, and iodide ions on oxidation produces iodine. So these are the two important reactions of oxidation of ozone. So let's see one by one. When lead sulfide on oxidation, lead sulfide PBS on oxidation in presence of ozone, it produces lead sulfate, and definitely the byproduct is oxygen. So this is the first reaction. Then the second reaction is iodide ions. If we are using potassium iodide solution and ozone, so potassium iodide solution is used, we will get the iodide ions in the solution is converted to iodine. So the iodide ions are oxidized to iodine and oxygen will be the byproduct. In these two cases, oxygen will be the byproduct, and in the first case, lead sulfide is oxidized to lead sulfate. Iodide ions are converted to iodine. So these are the two important reactions where we can see the oxidation by ozone. So using this equation, we can answer one other question, that is how ozone is estimated quantitatively. So how ozone is estimated quantitatively. So from this reaction we can answer this question. So that is, if we are using iodide ions, we will get iodine. So this liberated iodine. So from this equation we will get liberated iodine, or from this reaction the liberated iodine is used for titration. So this liberated iodine is titrated against sodium thiosulfate, Na2S2O3, sodium thiosulfate. So using this titration we can estimate ozone quantitatively. So this is a quantitative method for the estimation of ozone. So this liberated iodine is titrated against sodium thiosulfate. So from this we can estimate ozone quantitatively. Now let's see another 2 points, that is the threats. What are the threats of ozone layer depletion? So there are two important threats of ozone layer depletion. One is the nitric oxide which is emitted from the exhaust of jet aeroplane. So the nitric oxide NO which is emitted from the jet aeroplane, the exhaust of jet aeroplane depletes ozone layer. Actually it converts ozone to O2. So this is a reaction. Here this NO or nitric oxide causes ozone layer depletion. Another point is very familiar to you, that is freons. Freons in aerosol sprays and refrigerants. So these are the two threats of ozone layer depletion. The second one is freons in aerosol sprays and refrigerants. That is another threat of ozone layer depletion. Now let us see another important point, that is the structure of ozone. So you know how to draw the structure of ozone. So there are 18 valence electrons. We can arrange all these valence electrons with 3 oxygen atoms. So two, 4, 6, 8, 2, 4, 6, 8. So this is the first structure. So we can draw resonance structure in the case of ozone. So the next resonating structure is, here there is a single bond, here there will be a double bond. Here this is the second structure. So there are two resonance structures are possible in the case of ozone. The resonance hybrid can be drawn like this. The resonance hybrid can be drawn like this. So this is a resonance hybrid. So from this resonating structures, it is clear that the oxygen-oxygen bond length, they are identical. So oxygen-oxygen bond length are identical. So they are identical. So that may be 128 picometer. So it is 128 picometer. So it is identical. So this oxygen-oxygen bond length and this oxygen-oxygen bond length are identical because there is resonance. Since it is resonance, it is the resonance hybrid of two forms. Two resonating structures are possible. So it is a resonance hybrid of these two forms. So we can say the oxygen-oxygen bond lengths are identical. That may be 128 picometer, and the shape is angular, and the bond angle is 117 degree. So here also we can expect a question, why there is identical bond lengths in the case of oxygen. Why oxygen-oxygen bond lengths in ozone are identical?